I was coming to this meeting, and I couldn't help to think of like these two things that, I think that as humans we should be thinking about this and sort of taking it as, as an inspiration towards the future. The first thing that dawned on me was that we are the generation in human history that is going to be remembered in the future as the ones who found the first exoplanets. That's a fact right now. That will happen. Now, the question is, are we going to be also the generation that will be remembered by being the first ones that found life in those planets? So, I hope the answer is yes. And I'm going to show you here now how we are going to try to do that. So this slide, you have already seen it. You have already seen from previous talks that we are already starting to find the first potentially Earth-like planets. From Courtney Dressing's talk, we can even do numbers now. Courtney said that 1 out of every 4 small stars should have a planet. So based on those numbers, and if you look at this picture, which is the number of stars within 30 light years from Earth, you see that we have about 250 of them, which are those small stars. So if those numbers are true, we know that there will be about 60 planets out there that can be potentially like Earth. And that's just around the corner from us, 30 light years. So we know that this will happen eventually. We know that we will find all these planets eventually. Now the question is, how are we going to find the atmospheres? And I'm going to show you how we are going to do that. We know that for Proxima b, hopefully we can get there with the breakthrough Star Shot initiative, but these other planets are going to be farther away, so it's going to be very, very hard to do this. So the way that we are going to do it is sort of like an indirect way, but we know how to do it. We know that when the light from a star reaches a planet, the light can either be absorbed by the atmosphere of the planet or reflected or transmitted through the atmosphere. Some of that light is going to interact with molecules in the atmosphere. And when we look at the transit or even the reflected light, and we disperse that light into the different colors, what we call a spectrum, we see that there is some colors that are missing. And by looking at the wavelengths of those colors, we can tell you exactly what chemicals are in the atmosphere. In this case, this particular planet has water, has carbon dioxide, and has methane at 1.8, 2.1, and 2.3 microns. We can do this with every single chemical, either atom or molecule that you can think of. So this is how we are going to do it. Which atom and molecule are we going to look for? Which biomarker are we going to look for? David Caitlin already showed to us the answer, right? We're going to look for oxygen. But I wanted to show it to you in a much like a striking way, right? So right now we have measured the atmospheres of 3 Earth-like planets, like very, very precise observations of those atmospheres. Unfortunately, they are all just around the corner in the solar system. They are Venus, Mars, and Earth. So you see immediately, you see a big difference in the atmospheres of these 3 planets. You see it, right? There is a lot going on Earth that is not going on Venus and Mars. Earth, for one, has water. We know that we need water for life to exist, but we don't know if the planet is going to have water, but life has not kicked in yet. Oxygen, on the other hand, tells you that there could be life like ours on that planet, because we know, if we go back in time, even though the Earth had water, oxygen didn't appear in the atmosphere until life appeared on Earth. I know that there is some false positives that people are talking about, but right now there's four possible ways to do this. So to me, this is like you're playing the lottery and you have a 25% chance of winning it, right? Would you buy a lottery ticket? I would say, I would. So this is how we are going to go after oxygen at 0.76 microns, which David showed already. The way that we are going to do this is by using this technique called high-resolution spectroscopy. This technique is applicable to both transiting planets and non-transiting planets, but I will let Marcus Kasper explain the non-transiting case, and here I'm going to focus on the transiting planets case. What we do is when the planet is going in front of the star, part of the light is going through the atmosphere, So as I said before, we take that light and we disperse it into colors. If we look at a particular wavelength where the oxygen is meant to be, we see this very, very clear pattern at the bottom, which is like individual absorption lines from the oxygen. And the reason why we want to create a highly dispersed spectrum to look at the individual absorption lines is because we know exactly how those absorption lines look. And it's easier for us to detect oxygen if we know exactly what the pattern is. If you do this in low resolution, you just see one dip. It could be a systematic, you never know. But if you do it in high resolution, you can follow a given pattern and actually detect the oxygen in your planet. So what we have to do in principle is just we take the pattern of the spectrum of oxygen in our atmosphere, that we know how it looks like, look at the data from this planet, and try to cross-match that pattern and see if we can detect the oxygen. That's how we are going to do it. Sounds simple, right? There's always a trick, though. And the trick in this case is that the atmosphere of Earth, or any planet like Earth, is going to be that tiny little ring that you see at the top that is only about 1% of the size of the planet. And what happens in this case is that because it's only 1%, the size of the signal of oxygen that we are looking for is about 1 part in a million. If you convert that into photons, that means that you need to collect at least 1 trillion photons to actually detect an oxygen signal at a 3 sigma level, or in other words, with a 99% confidence. There is no telescope that we have today that can do this on a reasonable amount of time. You can maybe do this with an 8-meter telescope, but it's going to take about 60 years to do it. So now, how are we going to solve this? Well, the fact is that we are already working on it. You have probably heard about the extremely large telescopes. There is 3 of them, a European one, the European Extremely Large Telescope, and 2 American ones, the 30-meter telescope and the Giant Magellan Telescope. I'm part of the Giant Magellan Telescope group, and honestly, I don't know what's going on in the other 2, so for the rest of the talk, I'm going to focus on the Giant Magellan Telescope, or so-called the GMT. The Giant Magellan Telescope is a 25-meter telescope, which we are building at the Las Campanas Observatory in Chile. Just to show you the size of that thing, that's a 50-meter in length semi-truck, so it looks tiny. The assembly is going to be 7 primary mirrors, and then 8 meters in diameter each, and 7 small mirrors to focus back the light into the instruments. And we are assembling all of them, as we speak. And then the whole construction, the mechanical structure, the mirrors, and the enclosure, we hope to have it finished by 2024. We are also building at the Smithsonian Astrophysical Observatory the first instrument for the Giant Magellan Telescope. This instrument is called GCLIF, which stands for the Giant Magellan Telescope Consortium Large Earth Finder. And this is an optical high resolution, 100,000 in resolution spectrograph that covers in wavelengths from 0.35 microns to 1 micron. That includes the 0.76 micron band of oxygen that we are looking for. And we are slightly changing. So this instrument was initially going to be built to detect the wobble of the star, to find the planets themselves. But we are changing the design slightly to also make it an oxygen finder. This is going to be, GCLIF is going to be the first instrument of this class in any extremely large telescope, and hopefully we can start doing this type of observations within a few years in 2024. So 2024 sounds like it is just around the corner, but it's actually, time goes by very quickly. So there is a lot of activity going on already on this project. We're building the mirrors at the mirror lab at the University of Arizona in the campus in Tucson. There is already one mirror finished, and we have the other 3 mirrors at different stages of the way. We are also building the site in Chile. This is a drone view of the site back in February, where you see that we have already laid out all the roads to take all the pieces up there. And we have flatten the mountain already to make it ready for the telescope to go on that side. And then at the same time, in Cambridge, Massachusetts, in the in our labs, we are putting together G-Cliff. So in the meantime, our group and other groups around the world are working very hard on finding the actual planets because we don't have all of them yet. And I wanted to highlight here, a few projects. The Mirth and the TRAPPIST project are being shown in this meeting, so I will not go much more into them, but they are looking for transits around M-dwarfs. There is also the TESS satellite mission, which is going to be launched in about a year, and that one is currently being built in the lab. And hopefully, if everything goes well, in March 2018, it will be up in space. And if everything goes well, from the numbers that we expect that these projects will find, by 2024, we already will have the prime candidates to look for oxygen on them with all the ELTs. So these are the predictions right now. We have done the numbers, and some people already have given similar numbers here, but I will walk you through them to show to you how this is going to be a little bit difficult, but not impossible to do. So we know that one or more transiting planets will be found by one of these missions within, I'm talking here within 30 light years from Earth. We're going to find at least one transiting planet. Most likely, those transiting planets are going to be orbiting stars, so they're about 20% the mass of the Sun. Funny enough, LHS 1140 is one of those planets. So this is showing that that finding is showing that these statistics are close to correct. The advantage of finding planets in the habitable zone around these small stars is that those planets transit around the star every 26 days. If we were looking for a planet, around a G-dwarf, it's not only that the star is bigger and the signal is smaller. It's to get one transit, you would have to sit for a year and wait. In the meantime, you can get 14 transits on these targets. And at the same time, each one of these targets is going to last 2.1 hours. So we really have a narrow window of time where we can collect the light that goes through the atmosphere, but that's OK. Doing the numbers for a system that is halfway away in that volume that I'm telling you, like 15 light years away. So we could get there in 15 years if we manage to go at the speed of light. We would need 72 hours of Giant Magellan Telescope time to do this. That's not crazy. The problem is that those 72 hours can be collected only if you observe 32 transits, and every transit you have to wait 26 days to do it, so years. So that's where this actually becomes a little bit more tricky. And in addition to that, because you have these telescopes on the ground, they are not in space, we probably can only catch 1 out of 3 transits. The transit happens during daytime in Chile, the weather is cloudy, whatever it is. So overall, we estimate that if we were to do this just with the Giant Magellan Telescope, it would take about 5 to 6 years to collect the 1 trillion photons that we need to produce a 3 sigma detection. So here comes the call. We need all the ELTs to work together to bring this number down, because right now we are photon limited. If we can point the 3 ELTs with similar instruments to G-Cliff to the same target, we can probably bring this number down to 1 year. It will take us 1 year to detect oxygen in one planet. There is a possibility, that was also mentioned earlier, that the planets are not transiting. Let's don't panic yet, okay? If the planet is not transiting, the only problem here is that we're going to have to look at the reflected light coming from the atmosphere of the planet. And this is a little bit trickier to estimate how long it is going to take, because you don't know what the reflective properties of the atmosphere are, and you don't know what the actual inclination of the planet is, so you don't know what fraction of the atmosphere you're actually seeing the reflection back towards you. That's the bad side. The good side is that you don't have to wait for a transit, but you can actually look at the reflective side for at least like 1/3 of the orbit when the planet is sort of like smiling at you, right? So if you do all these numbers, my estimation right now is that it will take somewhere between 100 days and infinity to detect oxygen in a non-transiting planet. And the reason why I say infinity is because imagine that we have a perfectly clear atmosphere with no clouds. Then it will be very hard to get reflection back from that atmosphere. But still, if we have an atmosphere that is as reflective as Earth or a little bit more reflective, it might only take us about 100 days. And this is just with a GMT. Again, if we put the 3 ELTs together to work, this is going to take a month to do. So I'm going to leave you with all these ideas here. This is, food for thought. And I'm going to finish, and then I wanted to highlight that transit might be easier to do, but don't worry about it. So I'm going to give you with this thought that is like, sort of loops back to the beginning of the talk that says, will we be the first generation to do this? And the answer is maybe. Maybe we will. Maybe, in 10 to 15 years, we will have another planet that, humans can go and breathe in there. And maybe, as the Breakthrough Starshot Initiative is trying to do, maybe we will know which planets we're going to send those sails to and, just look. So thank you for your attention, and I'm open to your questions.
For a couple of questions.
Guyon,
Hi, I'm Guyon from Guyon. So when you made the numbers for the reflected light,
yeah.
Did you just integrate all the light into a single fiber, or did you assume some spatial information there where we can at least cancel out, let's say, a couple of orders of magnitude of the stellar light due to spatial resolution?
Yeah, well, I'm actually taking that into account. So, I'm assuming that we're getting all the light from the planet by, any technique. But, I'm assuming that we have gotten rid of all the stellar light. Then the reason why my numbers change so much is because let's see, I'm going to show that. The reason why my numbers change so much is because I take into consideration, a number of factors. First, the inclination of the system, so we could only be seeing like 30% of the surface. Then I take albedo into account, which is, how much of the light is being reflected back into space. Then I also take into account the amount of time that you need to wait for the planet to be back in a position where you could actually see enough reflected light. And I take into account the distance as well, the distance of the system. But in principle, yeah, so those numbers, if we have any contamination from the star itself, those numbers might go up a little bit. Yeah. Clara?
Hi, Clara Souza of MIT. You mentioned that the Giant Magellan Telescope could be kind of like an oxygen finder. But in that wavelength region, there's a bunch of other cool molecules, I presume. What are your prospects for finding them with the same data? How do you feel about the prospects of finding other molecules in that exact same region?
Yeah. So in principle, with the wavelength range that we are going to cover from 0.35 to 1 micron, we would only be sensitive to oxygen, and we would be sensitive to a little bit of water, close to the 1 micron wavelength. We are looking into how to detect water. I have people doing some simulations for it, and the one thing to worry about the water is that if the planet is truly like Earth, most of the water is going to be sitting within the first 10 or 12 kilometers from the surface. And unless the planet is orbiting a very, very small star, we will have refraction. Snell's law, the refraction index going from one medium to another. So what happens with refraction is that we will not be sensitive to about the first 10 kilometers of the atmosphere of any planet in the habitable zone. So if that happens, we cannot see water. So I cannot think of any other molecule right now other than water and oxygen that we can see. We probably can see some ozone, but the signal is going to be very, very shallow. So yeah, I don't think that there's going to be anything else there. So.